Students, in last class we discussed about the current components in the BJT. Then after how the BJT is acting as a amplifier. Today we will discuss about the different types of configurations. First of all, configuration is nothing but how the three terminals of transistor are used in a circuit such as amplifier. So we said the main application of the BJT is amplifier. How the three terminals of BJT can be connected or used as amplifier. So here we are having the emitter, base, collector are the three terminals. So you can observe the diagram in this slide. So here the three terminals are named as 1, 2, 3. So the third terminal 3 is common node. Yes. So based on which terminal is connected to the common node, based on that we define the configuration of the transistor. So when you are connecting the base as common node 3, then input terminal node 1 as emitter and output node 2 as collector. So this configuration is called common base configuration. We are connecting the emitter terminal at common node 3, then input node becomes base and output node becomes collector. This way of connection, this configuration is called common emitter configuration. And third one, when you are connecting the collector at common node 3 and input node 1 as base and output node 2 as emitter. This configuration is called common collector configuration. So we can configure the BJT in three ways. When I connecting the base as common to the input and output, then it is common base. When you are connecting the emitter common to the input and output, then it is common emitter. When you are connecting the collector common to the input and output, then it is common collector. So in this diagram, so when you are connecting the common node any one of the terminal, that node 1 and node 2, it is looking like a two-port network. This input voltage we are naming as V1 and input current I1. Similarly, output voltage V2 and output current I2. These are the voltages and currents in the BJT configuration. These input current, input voltage and output current, output voltage, these four are interdependent values. Their independence can be represented in the form of VI graph, which are known as BJT characteristics. While plotting the BJT characteristics, it is assumed I1 and V2 are interdependent parameters, whereas V1 and I2 are considered as dependent parameters. So V1 is a function of I1 and V2, I2 is the function of I1 and V2. So here we can draw the VI characteristics between input voltage and input voltage and input current, while maintaining the output voltage as constant, or otherwise we can draw the VI characteristics between output voltage, output current, while maintaining the input current is constant. So based on that, we divide the characteristics of BJT two types. One is input characteristics. In this, we will draw the graph between input voltage and input current by considering the output voltage as constant. And second one is output characteristics. Here, we will draw the graph between the output voltage and output current by considering the input current as constant. Yes, these are the two VI characteristics of BJT, that is input characteristics and output characteristics. First, we'll discuss about the common base configuration. So it is already discussed in previous. We consider the base terminal is common to the both input and output, and emitter terminal is connected to the node 1 and collector terminal is connected to the node 2. So in this configuration, the input is applied between the emitter and base, and output is taken from the collector and base. Here base is the common to both input and output. Hence this configuration is called common base configuration. Common base configuration of NPN and PNP transistor. Yes. So we already know the main application of the transistor is amplifier. To make a transistor as amplifier, we must operate this transistor in active region. So in this active region, emitter junction is forward biased and collector junction is in reverse bias. Yes, for the NPN transistor, so we need to connect the negative terminal of the battery to the emitter N-type material and positive terminal of the battery to the P-type material. Then emitter junction is in forward bias. To make the collector junction in reverse bias, the positive terminal of the battery connected to the N-type collector and negative terminal of the battery is connected to the P-type base. Now this collector junction is in reverse bias. So we can say this NPN transistor is in active region. Emitter junction is in forward bias and collector junction is in reverse bias. Similarly, PNP, it is opposite to the NPN transistor. In this common base configuration, the collector current IC is given by what we can write? IC injected plus IC BO. Yes, IC current is nothing but the charge carriers crossing at the collector junction. We can say the current due to the injected carriers from base to collector, and ICBO is nothing but reverse saturation current because the collector junction is in reverse bias. So the total current at the collector junction can be written as IC current due to injection plus ICBO. Here ICO or ICBO is nothing but reverse saturation current of collector junction, and IC is nothing but it is injected collector current due to the electrons crossing the collector junction. Yes. So this ICBO is the reverse saturation current. It is very small compared to the injected carrier current. So sometimes we may neglect this ICBO. So we can write IC equals to IC injection. Current amplification factor in the common base. Here current amplification is defined as output current to the input current. Yes. So we can say output current is nothing but collector current, input current is nothing but input current. So it's the ratio of output collector current to the input emitter current. So alpha DC can be written as IC by IE. So your IC almost equals to IC due to the injection carriers. Carriers. So we know the total current in the transistor can be written as IE equals to IB plus IC. So from that we can say this IE value is more greater than compared to the IC. Compared to the IC is small compared to the IE. the value of alpha DC, it is nothing but current amplification factor, is always less than unity. Why? Because the IA is the more compared to the IC, but it is always ranging from 0.95 to 0.995. So we know the base current is very small, IB is very small, so IC is almost equals to IE. So this alpha is varies from 0.95 to 0.995 depending on thickness of the base region. That means the width of the base region. So the current gain in common base configuration can be calculated by knowing the collector current and emitter current. So we know IC equals to alpha DC into IE plus ICBO. So ICBO is very small, it is a reverse action current, so we can neglect that one. From that we can write IC equals to alpha DC into IE. So we know current amplification factor in the common base we are represented with alpha DC, or sometimes it is alpha, nothing but IC by IE. We know total current in a transistor IE equals to IB plus IC. So from that we can write base current IB equals to IE minus IC. So I am replacing the collector current IC with alpha DC into IE plus ICO. From this we can write IB equals to 1 minus alpha DC into IE. Okay? First about the input characteristics of common base configuration. So input characteristics is always drawn between the input voltage and input current when considering the output voltage as constant. So we know here input current is nothing but emitter current I, and input voltage is nothing but VEB. This VEB is for NPN PNP. Here I am keeping the mod value, so you can use positive and negative for the different NPN PNP. So here input characteristics in CB common base configuration is drawn between the input voltage VEB and input current IE at constant collector base voltage VCB. Clear? So you can observe the input characteristics of a typical transistor in common base configuration. Yes. So it is looking like your normal PN junction diode for bias characteristics. Yes. So the input resistance of the common base configuration can be defined as what we can write input voltage to the input current. So the input resistance can be defined as change in the input voltage to the change in the input current by considering the output voltage as constant. It is Ri equals to delta VE by delta IE at constant output voltage VCB. So I said it is looking like our forward bias diode characteristics. So here you can observe the cut-in voltage of the diode. So or you can say base and emitter acts as a one diode. Yes. After the cut-in voltage, the emitter current IE increases rapidly with increase in emitter base voltage. Yes. So here VCB is the positive for NPN transistor and negative for PNP transistor. On the other hand, VEB is negative for NPN and positive for PNP transistors. Okay? Characteristics. So we said output characteristics always drawn between the output voltage and output current by considering the input current as constant. So the output characteristics of common base is drawn between the output voltage VCB and output current IC. Again, I am taking the mod value, so you can draw between the for NPN and PNP transistors. You can consider for anyone. Yes. So the output characteristics has three basic regions that are active and cutoff and saturation region. Yes. So here you can observe the active, cutoff and saturation region in the CB output characteristics in the figure. Clear? So active region is defined when emitter junction is in forward bias while collector junction is in reverse bias. We already know this one. Yes. So in this region, IC is approximately equal to the IA. That means collector current is approximately equal to the emitter current. In this case, the transistor is acts as amplifier. So when the transistor is in active region, then we can say the transistor can act as a amplifier. Yes. So in this we can calculate the output. The dynamic output resistance is nothing but output voltage to the output current. So here we can write change in the output voltage. It is nothing but delta VCB by changing the output current. That is delta IC by considering the input current I equals to 0. The collector current IC is almost independent on collector base voltage VCB. Yes, the collector current IC is almost independent of the VCB voltage collected to base voltage, and transistor can be said to work as a constant current source. Yes, how? Here the collector current is almost constant and it is not depends on the applied reverse bias voltage VCB. So it is providing the constant voltage and it is independent of the reverse bias VCB voltage. So this transistor can act as a constant current source. So this provides the very high dynamic output resistance. Why? Because this IC is not depends on the VCB, so delta VCB by delta IC is large value. Clear? Saturation region. We know in this region the emitter junction and collector junction both are in forward biased. So in this both the junctions are forward biased. The IC is independent of IE. Here collector current is independent of the emitter current and IC decreases rapidly with VCB becomes more negative. The collector current is decreased rapidly as collector to base voltage becomes more negative. Next, cutoff region. The region below the curve IE equals to 0 is known as cutoff region, where the collector current is nearly 0 and the collector junction JC and emitter junction JE of transistor are reverse bias. So when collector junction and emitter junction both are in reverse bias, then transistor is in cutoff region. In this, collector current is nearly 0 because emitter is also 0, so it is almost IE equals to 0. Yes. So in this common base configuration, the current gain, DC current gain, is defined as the output current to the input current. It is nothing but IC by IE. So it is noted with the alpha DC. Sometimes it is alpha. So alpha DC equals to alpha equals to IC by IE. Similarly, AC current gain, alpha AC, nothing but change in the output current to the change in the input current by considering the output voltage as constant. It is nothing but delta IC by delta IE. Thank you.